Okay, so with the Studio 3, let's see here. You're going to need to use a different form of VHDL, and we call that form of VHDL structural VHDL, or sometimes it's also called modular VHDL. So far what we were doing was behavioral. And in behavioral VHDL models, maybe I say code, in VHDL designs, how are they different from uh, structural? So in behavioral models, they are used for simple designs, and these are the ones in which you can easily express outputs in terms of inputs. And examples were 2-bit comparator, in which you had 3 outputs and I believe 4-bit input. So you were able to express the outputs, all 3 of them, as an expression, as a logic expression in terms of its inputs. And that particular expression was described using the signal operator, signal assignment operator. Right, so for example, if you had an AND gate, say A, B, C here, you said C, signal assignment operator A, and B, semicolon, and that was a very simple behavioral VHDL model. So this was Studio 0, in Studio 1, as well as in Studio 2. So far you guys have been doing behavioral VHDL codes. And this is okay as long as the design is simple and you can easily express the outputs in terms of input variables. Now, how about the structural or the modular VHDL? So on the left. So let me separate these guys out here and then talk about what's on the left here. So in the case on the left, suppose you have a hierarchy of models. So suppose you have, component 1, component 2, component 3, component 4. You have multiple designs. So you can call that module 1, module 2, module 3, module 4, and the entire thing can be called top level. So when you have a pretty complex VHDL design, such as the one that is shown over here using blocks, then you are better off using a structural or a modular VHDL design strategy. So what do you need to do first here? You need to design M1, M1, 2, 3, 4, and these can be again behavioral, or they themselves could be structural, which means there could be more modules inside the modules, which is fine. So but first you would have to design those 4 modules. How do you do that? Well, you talk about their entity, you talk about their architecture, right? So all 4 have to be designed first. Now, some of them might be unique, some of them might not be unique. So when I say design, I'm referring to all the unique components. So, we don't need to do this if M2 and M3 happen to be the same. We only do M2 then, right? So design unique components first. So once you do this first step, you have the VHDL design that goes into each of those modules. And once you're done with that, you have to write a new VHDL file called the top level, which is going to be used to put all these four together in the form of a modular design. So that's why you hear the term top level. Now, when you have a total structure, you are probably going to have some inputs here. In fact, I don't even have to do this. I can just say inputs to the entire thing, outputs to the entire thing. So these have to be discussed in the XDC file. So when you do the top level, that's what you talk about. The things that are inside the entity of the top level, that's what you have to attach to something physical on the FPGA board. So only those go on the in the XDC file, the Xilinx design constraints file. Not those. You will not have any of those inputs and outputs being connected. All right, let's see here. So the individual inputs and outputs to the modules, they need not be connected to the something physical. Although you might have something that goes like this, which means that an input to module 3 is also appearing in the XDC file, which is fine, which is okay. So after having done the first step here, designing each individual module, each individual unique model, the next step is going to be to put everything together, all the pieces of the puzzle. So first you get the pieces ready, then you put it together, right? And to put it together, you need some hints, right? You need some sort of a sketch to be able to guide you to put the pieces of the puzzle together. And that sketch will look something like this, and we call that the block diagram, right? So for example, in our case, for the 4-bit full adder, let me pull that up here. Let's see here, and studio exercises. Oh no, not this. This is the adder block diagram. So in our case, this is going to be that sketch that guides us to put things together, right? So that's the key. This is the most important document in the entire studio. So this will, so first what do you have to do? You have to design these, right? First step was to design these components. I already gave you some of these. These two are one component because they are two instantiations of the same display driver module that you in fact designed in Studio 2. So you don't have to write it twice, you just have to write it once. And in fact, I just gave it to you because you already did it in Studio 2. So that is available to you. The LED display component is used to interact with the 4 7-segment displays. There are 7 outputs in the segments that are going to the 7 lights that are arranged in that 7-segment display pattern. And then there is a 4-bit vector anodes that controls which 7-segment display that information goes to. And if you do this fast enough, as you can see here, we are using a clock input to the LED display, which is coming from the onboard clock. and then there is a 100 megahertz on-board clock on the FPGA board, and we are controlling, we are providing that as an input to the LED display component. So essentially what you're doing is you're switching between the 4 7 segment displays so fast that you are able to display different things on different 7 segment displays by doing that switching fast enough. So that's the magic trick here. Now coming back, so LED display is given to you. All you have to do is, the puzzle piece is ready. You just have to put it in together. Display driver 1 and display driver 2 are essentially two instantiations of the same component, display driver. So those are ready. But you have to design, in this one, you have to design one component, which is the bit full adder. And once you design that component one time, you have to instantiate it 4 times. So it's kind of like there is one puzzle piece, you get that one puzzle piece ready and use it 4 times. You don't have to do four new things. There is a question on the chat box, which is about XDC file and the clock input. Yes, everything that is appearing inside and outside of the dotted box here needs to be in the XDC file. So let me highlight that dotted box here. Now anything that you see that is outside of this, all of these things need to be connected to something physical. Hence, they need to be part of the XDC file. All the blue dots need to be in the XDC. But one key point over here is that bit full adder 0, 1, 2, 3, those are not 4 different components. Those are the same components. So you design once and then you instantiate it or use it 4 different times. In top level module, there are 3 key things. One is component declaration. So let me write down over here. Component declaration. And all of these things happen in the architecture of top level. This is before the begin. So component declaration is the first step in those 3 main steps which appear in the architecture of top level. And component declaration essentially means that I need to explicitly mention what unique components I'm going to be using, right? So explicitly mention or define all unique components being used. And the way you can do that is by going and looking at what are the unique components here. Well, 1, 2, 3. That's it. So you need to do a component declaration for 3 components. What does component declaration involve? It essentially is a copy paste of the entities of the respective components, unique components. So you would essentially copy paste the entity of bit full adder after you design it. You will copy paste the entity of display driver It is given to you. You will copy paste the entity of LED display. It is given to you. Note that there are two entities in the LED display. One is for MUX 4x7, which appears at the top. Don't use that. There is another entity in the middle of the code which is for LED display. You need to use that because that's the entity of the LED display. So all you would do is you would copy paste the entity, but then you will have to replace some key things. So you, instead of saying entity name and then what are the inputs, what are the outputs, at the end you will say end the name. So instead of that, component declaration, you need to change this. You need to say, instead of entity, you need to say component. And instead of end followed by name, you have to add end component name. So by making those two adjustments after you paste the entity in the top level, you can make those quick changes. And you have to do this for three things, right? Bit full adder, display driver, and LED display. That's it, component declaration. So you have told the VHDL compiler that, hey, when I put this puzzle together, I'm going to be using these three unique components. That's step number one. Step number two is signal declaration. And signal declaration is when you are connecting two components together, you might need an intermediate signal. So for example, suppose you are trying to connect this. Let me highlight in yellow. Suppose you are connecting the output of bit full adder to the input of this display driver. Then you need to declare a signal called S1. And once you declare the signal S1, what you can do is you can connect this particular output to S1. And when you put in the piece for display driver 1, you can connect the input here to S1. So connect the output of bit full adder to S1 and connect the input of display driver to also S1. That is how you make that complete connection, by using S1 as that intermediate signal. In other words, any output that you see over here that is not the final output should be declared as a signal. So you see there are so many outputs. I will highlight with blue. Output, 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 right? These are outputs of some components. Outputs, outputs. So all these outputs are that I just highlighted in blue. Those were outputs and they were not the final outputs. The final outputs are just these. So those don't need to be declared as signals, but any output that is not the final output needs to be declared as a signal, so that you can use that as an interconnection between output of one and the input of the other. So let me write that down. All outputs that are not the final output need to be declared as signals. And in the document I have shown you in the document some syntax as to how to do that. These two steps, component declaration followed by signal declaration, happens after you say architecture but before you say begin. After begin, you do the third step, which is component instantiation. So declaration first, signal declaration next, and then the third one is component instantiation, also called as port mapping. And that particular step is essentially this. You have told the VHDL compiler what are the different components you are going to use. You have defined all the signals. Now what you have to do is you have to bring in each piece of the puzzle and you have to make all the connections. So I will show you one example and you can use that to do everything else. So what I'll do is I will write one example for this. Let's see. Actually, I can just do this. How many times do you have to port map? You have to port map 1, 2, 3, 4, 5, 6, 7. 7 things. So you will have 7 port mapping statements. There's a question in the chat box. Let me take a quick look at that. Uh, Alan says, is there a way to find the actual variable values through the software? Like if I run my program, is there a way to see which switches are on and what the carryout values are? I don't think that there is a very easy way to do this. You will have a couple of options. What you can do is you can pull out those intermediate values and connect them to an LED and monitor the LED getting switched on or off, or you would have to write a test bench. So you would have to write a separate VHDL file which is essentially simulation of your VHDL design. We call that a test bench. So you can use that to verify how your design is working. So you can do a couple of things there. Carry in is an input. So I would it's in my it's an option for me to attach that to a switch. So I will include carry in the entity of the top level, and I will attach that to the carry in input for the bit full adder 0, and then later connect it to the switch. So I will show you how it is, right? So I'm assuming that these are in the entity of the top level. So let me see. Let's say I have entity of the top level here. And as I said, everything that is going in and out of that dashed box needs to be inside the entity of the top level. So you need to have, say, maybe you can say this is switch 0. You can say this as switch. Perhaps you can use this as switch 0 least significant, right? So you can do this. So if you have 1, 2, 3, 4 and 1, 2, 3, 4, 8 switches like that, and suppose this is 0, 1, 2, 3 and 4, 5, 6, 7. So you can use this for switch 0 and you can use this for switch 4. You can use switch let's see 1 here and switch 5 there, and so on. This has to be in the entity anyway. So you have switches here, top level entity, switches, it's a vector 7 down to 0 input. All those 8 switches are being used to provide the A and B inputs for each of them, like I showed. Switch 0 here, 0 here, 1 here, 2 there, 3 there, then 4, 5, 6, 7. So switches. After that, what do you have? You have carry in, clock, segments, and anodes. Carry in, just 1 bit, so standard logic input. Clock, just 1 bit input. Anodes output 4 bit, so 3 down to 0 output. Then you have segments. Let's see, 6 down to 0 also output. End, top level. So I would encourage you to use the wizard to get all the details in, so that you don't have any syntax errors. But I just laid out all the inputs and outputs of the entire top level, which is the dashed box here. So everything that is going in and out of that dash box needs to be in the entity of the top level. So given that, you have, after that, you have the statement called architecture. After that, you have the component declaration step. After that, you have the signal declaration step. In the signal declaration step, because I'm going to be doing component instantiation of bit full adder 0, I need certain declared signals. So for example, I need S0 and C0. So I'll just write that. S0, C0 are standard logic. That's it. Are standard logic. They could be 1 bit, they could be multiple bit. For now, this sum and this carry are just single bit. That's it. So after that, I have the begin statement and end. Inside the begin and end, you will have 7 different port mapping statement, one corresponding to one instantiation of a component. Because you have 7 different instantiations, you will have 7 different port mapping statements. I will show you one such example, how to port map bit full adder 0. So for what I'm going to do is, between begin and end, I'm going to, okay, let me do this. Edit and bring it over here, and then I will start with a label. Each port mapping statements needs to be labeled. So I will say label 0, followed by the name of the component that you are going to instantiate. In this case, I'm going to say bit full adder, provided this is the same name I used for it in the component declaration, followed by port map, followed by parentheses, semicolon. Inside the parentheses, I need to say what I'm going to connect to what, and I'm going to go from inside out. So for the sake of clarity, let me say this is C in, this is say A, this is B. Let me use some other thing. Let's see, this is, I can say this is input 1, input 2, this is carry out, this is sum. So I've literally named inside the component. So when I design that particular bit full adder component, I am assuming that those are the inputs and outputs names I used. So how do I connect in 1 to A? Well, I just say in 1 connected to A. And A should be here. Well, A is not here. So maybe I connect it to something else. let's see, this is going to be switch 0. If this is switch 0, comma, into connected to switch, what was it, 5, or no, 4, I think, right? What was it? Switch 0, 4.
It was
Yes,
4.
it is 4. Switch 4, and then what? C in is connected to carry underscore in, comma, what else? C out connected to C0, and then sum connected to S0. All of that needs to go inside the parentheses, separated by commas, and the port mapping operator is equal greater than. So it is going inside out. In one inside the component is connected to switch 0 outside the component. So all of these need to be here or here in the signal declaration. And you have to do that for all the 7 instances, 7 port mapping instantiations. This doesn't have to be one wire to one wire. You can do 7 wires at the same time. So if you define sig segments 1 as a vector 6 down to 0, you can connect that to the input of the LED display directly. You don't have to do one wire at a time. You can connect all 7 to all 7. Now in some cases you might have to connect it to 0 here, for example. What do you do then? For that case, what do? You say, when you are instantiating display driver true, you say, let me call this, maybe I can call this A, B, C, D, right? Suppose I wanted to connect B to 0. I would say B connected to 0. C, comma, C connected to 0, like that. I'm essentially forcing that to 0. And if you have more than 1 bits, so for example, for 6 segments 3 and 4, you might have to connect 6 zeros. So how do you do that? You say sig segments 3 equal greater than double quotes 1, 2, 3, 4, 5, 6, 7. 7 zeros. So that will make sure that those are off all the time. So that's forcing something to be on or off. And then after you're done with the top level VHDL design, you would write one XDC file for that top level, in which you have to connect these inputs, that guy, and those to something physical. All right, so I guess that's all I have for you guys. The rest of the things, the rest of the details, you can read up in the document, but I just wanted to go through this so that you have an understanding of what we are doing and why we are doing it. So I'm going to stop recording and then take questions for a minute.